Hi, I'm Harper and I'll be presenting our 2026 DAC demo. So what we demonstrate is an AES key recovery from the MCU of an Arduino Finder Opta, which is an off-the-shelf PLC. PLCs are commonly used in heavy industry, and since we demonstrate a vulnerability of the MCU on board this unit, this presents a potential vulnerability that could, if extended, maybe allow attackers to modify operations of the PLC in a high-stakes industrial environment. So here's a look at our hardware setup. What we have is the Arduino Opta pulled out of the case and also with the top board removed to allow us access to these pins. We have our Chip Whisper EM probe coming through a low noise amplifier and into the Chip Whisper Husky. And for these pins, we repurpose an LED pin to serve as an AES trigger signal. So that's this wire coming out, and then this is a ground. A look at our live TVLA visualizer, which we use to find a hotspot on the chip. The leakage is incredibly sensitive and only localized to a very specific part of the chip, so we needed a tool like this to find it. In particular, we were using a 3-group TVLA, meaning we have 2 sets of fixed plain texts and then 1 set of random plain texts. We compare the first set of fixed to the set of random as our standard TVLA test, and then we also compare the fixed to the second fixed set as a null control to ensure capture order differences are eliminated. And so you can see here, we're localized over that part of the chip, over our hotspot, and we have meaningful leakage appearing. And here's a look at what happens when we pull it out. We reset our trace accumulation, and we start just accumulating noise. So since there's no leakage anywhere here, it's just pure noise, we're not gonna see any leakage happening, anything crossing the T-curve threshold, and our line here of max T is just flat, pretty much. So now we'll quickly be demoing our capture script. We're just capturing a few things here. You'll see it initialize, capture 200 traces, and what we actually do for our full data set is capture approximately 2.5 million fixed key traces, and then approximately 120,000 random plaintext traces. Then this is now a look at a figure we get after running our profiled template attack. And so in the left graph, what you'll see is guessing entropy converging down towards 0. It does not directly reach 0. We do not fully recover the true key just from the profiled template attack, but it gets us nicely within range of enumeration. And that's what's shown over on the right. You can see we've pulled various, about a range of true rank values at which the key might be enumerable, and our profile template attack converges comfortably below that. We also demonstrate where CPA ended up on both of these metrics, and you can see the CPA mean lands at about 6 and at about 2 to the 50 in terms of rank, which means it is right at the upper bound of where it might be practically enumerable with a lot of computational power, but at least for our purposes, the true key was not recoverable with CPA. So then after we get our true key rank within range where enumeration can work, we then run enumeration, which this will show. And then it does take like a minute, so we'll just cut this middle. And as you can see, we enumerate first half of the key, second half of the key, and after around 111,000 candidates, we reach recovery of the true key. In this case, our effective key rank of the true key was right around 2 to the 16.8, but we were able to recover it with enumeration. So in summary, we've demonstrated AES key recovery from the microcontroller unit on this PLC. Since PLCs are commonly employed in important industrial applications, any sort of hardware vulnerability on these can be high stakes. One proposed mitigation we might implement is time randomization, inserting random operations in between the standard AES operations to mask leakage. And for further attack work, this is an assembled PLC. If we get a smaller EM probe, we might be able to insert it and grab leakage off of an assembled PLC.